So now let's turn to the model summary. By running the summary of our GLM object, we get an output that, again, similar to everything we've seen before, but the same as with the log normal family GLM that we ran. These estimates of the coefficients are not actually in real-world values. These are transformed estimates, right? They're on the link scale. They're log scale numbers. You'll also see that there are 3 of them, right? Because we've got 3 categories. What we've just run here is kind of similar to an ANOVA type of test, where you get these three different coefficients, right? The intercept, in this case, is being assigned the Alaska location, and then we've got a coefficient for Japan and a coefficient for Ohio. This is just like an ANOVA that we ran before, right? It's treating each of the different categories that we've got. If we had more categories, more locations, there'd be more coefficients, one for each of them. And so this is similar to an ANOVA in that we're running a type of linear model on a categorical predictor variable. But this isn't called an ANOVA. An ANOVA is specifically for Gaussian data. It's specifically for that LM function. And now that we're doing a GLM version, this isn't an ANOVA, but it's an ANOVA type test. You could do the same thing with a t-test or a t-type test, right? A t-test is for the LM function. But since we're doing a GLM, if we were to run a GLM version of a t-test, it would look kind of similar to this, where you get a coefficient for each of your 2 groups. The intercept coefficient is for group 1, and then you get a coefficient for the second group. And so these are similar superficially to t-tests and ANOVA, and they're practically doing the same thing. They're just doing it without assuming normality, without assuming a Gaussian distribution. And so whenever you encounter all of these other cases of data that deviate from the assumptions of a normal Gaussian linear model, switch to a GLM, and you're still doing the same thing as a t-test or an ANOVA. You're just not actually able to call it one of those things, but it's practically the same. You're just better accommodating your data. Now, as I said, these coefficient estimates are on the link scale. They're not on the response scale. They're not on the real-world scale. And so if we wanted to actually interpret them, right, we need to do the inverse link function. Now, since we have a GLM that is specifying the link equals log up here, the inverse link function is an exponent, right? So if we have our GLM object and the intercept, right? The intercept as our summary output is telling us is negative 0.584. That is on the link scale. To get it on the response scale, we take the exponent of it, and it becomes 0.558. Right? Again, adding things together. If you wanted to then add in your other coefficient, you would do the same thing, right? Missing GLM coefficient 2, and you would multiply that times whatever your value of x is that you cared about. If you're trying to predict group 3, you would do something like this and run that. And again, this is very different than taking the exponent of your first coefficient and then adding it to the exponent of your second times the x data you're interested in. This is wrong. You can't do this. You cannot exponentiate each individual term and then add them. You need to add them together before you take the exponent. So that's just an important thing to remember. But of course, you can avoid all of this if you simply use the predict function, right? If we feed the predict function our missing GLM, and the new data object is going to take a data frame, as always, called location. Again, it has to be called the same thing as our predictor variable. And we want the location to be equal to Alaska, right? This is the same thing as specifying in our equation that we want to multiply our coefficient 2 and our coefficient 3 by 0, and then just take the exponent of the intercept. Right, so if we predict over our GLM using this new data where location equals Alaska, we specify type equals response, we'll get 0.558, right? Same thing we did when we just took the exponent of the first coefficient of the beta 0, beta naught, the intercept. And so that predict function is how you can estimate these things, right? You can switch from AK to JP. There's the predicted estimate for Japan. Same thing for Ohio, right? Specify that. You can use this predict function to just simply calculate these things. And by saying type equals response, you're saying give me the real value, not the log transformed value, which is type equals link if you wanted that. And so that is kind of how you can crack open the output of all of this and make sense for what you're doing here. Remember that this is an ANOVA type test, and if you had just two categories, it would be a t-test type test, but they're not really t-tests or ANOVAs. They're GLMs, they're generalized linear models on categorical predictor variable. And this is why I kind of stressed to you in the beginning not to get too caught up in what a t-test is or what an ANOVA is. Because they're all just linear models, and in this case they're all just generalized linear models. So being able to simply apply a GLM to your data will allow you to arrive at the same conclusions.